So in the last video, we talked about all our different variables in a gas. We talked about pressure, volume, temperature, and moles. Those are the 4 primary variables. Turns out if you know those things about a gas, you pretty much know everything you need to know about that gas. And so now what we're going to look at is how are those variables related? What happens to pressure if we change volume? What happens to volume if we change moles? Some of them are a little more intuitive than others, but hopefully we're going to get a sense of all of them as being somewhat intuitive. So pressure and volume. What is the relationship between pressure and volume? Well, you probably have a great experience of this if you ever have pumped a bike tire. And most of us, if we've ever pumped a bike tire, have also stuck our finger over the top of it, right? We have the little thing here, we just go like this, and then we push down on the cylinder, and what do we feel? Right? As we push down on the cylinder, it gets really hard to push down on that cylinder, and our thumb starts to feel this little push pressure too, and if we do it just right, it goes, right? Sounds kind of like an elephant. Why is that? Well, what are we doing? When we're pushing down on that piston, I can't draw to save my life, but we're going to try here. When we push down on that piston, there's a chamber here. And what we're going to do is we're going to make that chamber smaller. And so our volume went down. Now, as our volume went down, there's the same number of gas particles in there. Right? There's this many gas particles over here, and there's this many here. Now, if they're in a more cramped space, that means they're hitting the walls more often. It turns out it's when gas molecules hit the wall that we feel that pressure, that force over area. And so if you got your little tube over here connected to this, the pressure is going to be going up here because there's more things hitting the walls more often because they're scrunched in a smaller space. And so we found that as the volume went down, the pressure went up. And that's why we feel that at the end of our pump. How that works out mathematically, I'm not going to tell you all the details of it, but you end up with this equation that P1V1 equals P2V2. What does that mean? That means if we have a situation right here where we start, and we know that, let's say we've got a 2-liter container and it's at 1 atmosphere of pressure. If we multiply those together, we get 1 atmosphere times 2 liters, right? P1 times V1. That's going to be the same no matter what we do to it, as long as we keep a constant temperature and number of moles. Right? So we're going to change volume and pressure, but keep constant temperature and number of moles. As long as we keep those constant, no matter what we do to change the pressure or the volume, when we multiply them, it's going to be 2. And of course, it's going to have units of atmospheres times liters. So how does that help us? Well, let's say we knew when we changed the volume of this thing that we changed it down to 1 liter. But what we didn't know is what's the new pressure inside there? Well, all of a sudden we have this equation that allows us to calculate that. We get that 2 atmospheres times liters is 1 liter times P2, or that P2 is 2 atmospheres. Sorry. 2 atmospheres. And so we found out that as we took the volume down by half, the pressure went up double. As one goes down, the other goes up. So this is the mathematical relationship between pressure and volume. And what it does is allows us to calculate an unknown either at the beginning or at the end if we know all of the other conditions. So it doesn't matter what we're missing, P1, V1, P2, or V2. As long as we know the other 3, we can calculate the one that's missing. And it's a very useful thing to be able to do that. So this is called Boyle's law. I'm never going to test you on the names of these things, but it's good to know them because people use them sometimes. It's called Boyle's law. And we just did one where we reduced the volume from 2 liters to 1 liter, but let's see what happens if we keep reducing the volume. We've got gas in a 2-liter bottle at 1 atmosphere of pressure, and we're going to squeeze it and reduce it to 0.25 liters. Now, it's always a good idea when we're doing these kind of problems to get an estimate of, do we expect things to go up? Do we expect things to go down? And what are we doing? We're making the volume go down, which means the pressure is going to go up. And by the way, when we have a relationship between one variable and another variable, where one goes up and the other goes down, it's called an inverse relationship. Okay. Those are very common mathematically. So let's go ahead and set it up. And how I like to set up gas law problems is I like to write the equation that I'm using, and I encourage you to do this when you're doing quizzes, tests, homework, whatever. use this kind of strong format, and it makes it really easy to follow what's going on. I like to write the equation I'm using, then write out a table of my variables. It's really tempting just to start plugging things into that equation, but what quite often happens is that as you plug in those numbers, you mix up and you put the 2 liters with the 1 atmosphere with the 0.25 liters and not the right variables altogether. What I generally think of is these ones were the starting conditions, and these ones are my ending conditions. Although it doesn't have to be that way, it often works out that way really well. So P1, what was my starting pressure? Well, if you read here, we had a gas in a 2-liter bottle at 1 atmosphere of pressure, and so that's my start, is 1 atm. Remember, you use that shorthand sometimes for atmospheres. And my starting volume, what you have to think of is when it was at 1 atmosphere, and I should get my sig figs right? 1.0 atmospheres. When it was at 1 atmosphere, what was its volume? And if you read it up here, it says we had gas 2 liters and 1 atmosphere. And so we have to make sure those are at the same time. Both are number 1 here. Then number 2, we do something to it and we change things. What's our ending one? Well, we don't know the pressure because if you look, it says what is the pressure, right? That's the goal of this problem, is we're trying to find the pressure. But what do we know? We do know that the ending volume was 0.25 liters, so we can put that one down here, 0.25 liters. Now, once you've done that, then you can start substituting things in. And there's 2 ways to do it. One is to solve the equation first and then plug in the numbers. The other is to plug in numbers and then solve the equation. Doesn't matter which way you do it, whichever way is more comfortable for you. I kind of do it both ways depending on the problem, but let's go ahead and solve this first. What are we solving for? We are solving for P2. So I write out my equation. And then how do I solve this for P2? Well, I've got P2 over on the right. I need to get it all by itself. So I divide both sides of the equation by V2. And I get something that looks like that. They cancel over there. And I get that P2 equals P1 V1 over V2. And now I can just plug in those numbers straight from that table I had up on top. P1 was 1.0 atmospheres. V1 was 2.0 liters. And then V2 was 0.25 liters. And if you do that math, you end up with 8.0 liters as, I'm sorry, 8.0, not liters, as my final pressure. Now, that was a great thing I just did, is I wrote down 8.0 liters, and I thought to myself, well, that's not my final pressure, because my pressure should have pressure units. And it happens. I mean, I've been teaching this class for a long time. I know the answer to this problem. I've been teaching this problem for a long time. But what did I do? I wasn't really paying attention. I made a mistake on my units. It happens to all of us. And it's going to happen to you. So it's always good to double check and say, hey, I wrote liters there as liters a unit of pressure, and be like, oh, no, it's not. There's something wrong with what I did. And I look back and my liters cancel. And just as I should, I'm left with atmospheres. And so I found that as the volume went down, the pressure went up. So that's our relationship between pressure and volume. So here's a chance for you to try. We've got a container filled with 3.5 atmospheres of gas. It's shrunk down to 5 liters, and the pressure goes up to 8.5 atmospheres. And we want to know, what's the initial volume of the container? What did it start at? So again, a good chance to pause and try this out for yourself. Alrighty. What do you do? Well, on a test or quiz, you're not going to know which equation to use because we're going to see some other equations. So one thing I always do is kind of circle my numbers in there, or even write them out separately. And what do I have? I've got 2 pressures and I've got a volume, and I've got nothing else. I don't have any temperatures, I don't have any moles. So that tells me I've got to be using something that relates pressure and volume. So I start with that equation. I make my little table. Looks something like that. And what's my initial pressure? Right? It's filled to 3.5 atmospheres. That's my initial, 3.5 atmospheres. And I don't know the initial volume. It says it's shrunk down, which means I was never told the initial volume. And if you look at the end, it's actually asking, what's my initial volume? So that's my question mark. P2, my ending pressure is 8.5 atmospheres. And my ending volume is 5.0 liters. Now I can certainly plug those in and work to solve the problem. One other thing you can always pay attention to with multiple choice problems, right? You have all these answers there. Are there any we can eliminate without actually doing the math? Well, if we know that the container was shrunk to 5 liters, what does that mean? It means it started off at bigger than 5 liters. So without doing any math, we can actually cross off 3 of those numbers. And even if you're guessing, you now have a 50-50 chance instead of a 20% chance. That's much better. But let's go ahead and do it properly. Let's go ahead and put the numbers in first this time and then solve. So we're going to write 3.5 atmospheres times V1 is 8.5 atmospheres times 5.0 liters. How do I solve that? I need to get V1 by itself. So in my next step, I'm going to divide by 3.5 atmospheres. That's going to cancel. I've got to do it to both sides, 3.5 atmospheres. My atmospheres are going to cancel. They're going to leave me with liters as I want. What I type in my calculator is just the numbers, 8.5 times 5.0 divided by 3.5. And if you type that into your calculator, let's go ahead and do that. Okay, 8.5 times 5 divided by 3.5, I get myself 12.14. Now, what are my units? Well, I decided my units were liters up here, so is that correct? Yes, I'm looking for a volume, and I got liters. Now I have to worry about significant figures. All of my numbers that I started with have 2 significant figures, and so my answer should have 2 significant figures, and I get 12 liters, which is answer B. Make sense? All right. What's our next relationship? Our next relationship is between temperature and pressure. Remember, temperature is a measure of kinetic energy. When things are cold, they're moving very slowly. And when they're fast, moving like molecules are moving back when they're really, really fast. So if we have something that is a low temperature here, and we've got little molecules in there, they're just kind of meandering about, and they hit the walls every once in a while. And remember, I told you that it's the hitting the walls that actually makes us feel the pressure. If nothing ever hits a wall, then there really is no pressure, right? So we get those things hitting the walls every once in a while. But let's go ahead and speed those up now, right? So we have that same guy, but now he's moving like this. And right, how long did it take us? About 1, 2, 3, 4. 4 seconds here to do those 2 little bounces. Now, obviously, I'm exaggerating. Gases move much faster than that. But let's figure it out now. If I make this a high temperature and everybody's moving really, really fast in there, in my 4 seconds, 1, 2, 3, 4, whoa, I hit the walls like maybe 100 times because I had high temperature. This thing I was zooming around, zoom, 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 zoom. And every time he hits the wall, that's pressure. And so, excuse me, I've got a lot more pressure in this one on the right because I'm hitting the walls. And not only am I hitting the walls more often, I'm hitting the walls harder because the faster you are, the harder you hit the wall. I mean, imagine running to a wall at 50 miles an hour. That's going to hurt you. But if you run into a wall going at a snail's pace, you're probably not going to get hurt that much. So faster hits the walls more often, faster hits the walls harder, and our pressure is much higher here than our pressure is here. So we've got a large pressure. So as temperature went up, as we increased the temperature, the pressure also went up. That's opposite than what we just saw with pressure and volume. This is what we call a direct relationship. When one goes up, the other goes up. Direct relationships, they have different mathematics behind them. Remember before we got P1 times V1? Here we're going to get P1 over T1 is equal to P2 over T2. We actually divide those 2 different variables. And this is our relationship between pressure at the start and temperature at the start, and pressure at the end and temperature at the end. And we're going to use that in order to calculate how pressure changes with temperature and things like that. Now, why might you need to do that? Well, you might need to do that. If you ever read an aerosol can, what does it say? Do not put in fire. Why? Because as you increase the temperature in there, you're increasing the pressure, and in that sealed container, eventually it's going to burst and explode, which is not really what you want it to do. So let's go ahead and do a sample calculation with that. If anybody ever asks you about P1 over T1 equals P2 over T2, it's called Gay-Lussac's law. And we're going to say we've got a sealed container with 1 liter of volume. Again, we're going to focus on our numbers with units, and 3 atmospheres. It doesn't say pressure, but we know that atmospheres is a pressure unit. 100 degrees Celsius, and we cool it to 0 degrees Celsius. Now, this gets a little harder because we actually are given a volume, a pressure, and a temperature. But look at what the question's asking. It says we cool it to 0. So we see that there's a change in the temperature. So we have an old temperature and a new temperature. And they ask us for the new pressure. So we know there's going to be a change in pressure from the old pressure to the new pressure. But nobody mentions volume. And if nobody mentions it, chances are it's not changing. And that's just additional information given to you. And you're like, Professor, don't give us additional information. We're struggling with the information we have. But remember, that's not what life does. Life throws all sorts of information at you. You have an entire internet full of information. And your job is actually not so much anymore just to plug in the correct numbers in the correct places. Your job in this day and age with all the information at your fingertips is to know what's the good information and what's the not good information. So that's part of what we do here is we practice those skills. All right, so we now decided that pressure and temperature are changing. We know we're going to use this equation. P1 over T1 equals P2 over T2. What I'm going to do, I'm going to make myself a little table. And I've got P1, T1, P2, T2. What's my starting pressure is 3.0 atmospheres. And when it was at 3 atmospheres, what was its temperature? It was 100 degrees Celsius. And then I cool it down to 0 degrees Celsius. Oops, I put a 1 there instead of a 2. I cool it down to 0 degrees Celsius. And I'm actually asking for my new pressure, so that is what I get there. Now, it's always really tempting once you get this table to just start plugging things in. So let's go ahead and do that. We did not resist the temptation. And we end up with 3.0 atmospheres divided by 100 degrees Celsius. And we get P2 divided by 0 degrees Celsius. Now, hopefully at that point you looked and you thought, I remember having a math teacher, maybe lots of math teachers, that told me dividing by 0 was a bad idea. So how can Professor Clements be dividing by 0? Well, we aren't actually dividing by 0, because remember, I said a couple things. 1, what temperature unit are we going to use on all of our calculations in gases? We're going to use Kelvin. And the reason is this. Celsius is a made-up scale. If temperature is a measure of kinetic energy, then when temperature is 0, there should be no kinetic energy. There should be no motion whatsoever. But 0 degrees Celsius is not where there's no motion. There's lots of motion still at 0 degrees Celsius. And so that's why we have to convert everything to Kelvin, is because it actually shows us when Kelvin is 0, then there actually is 0 motion. Kelvin. So what do we have to do? We have to add 273. So if our little table here, T1 is 373 Kelvin. T2 is 273 Kelvin. And then we plug it in. Again, we can always plug in then solve, or we could solve and then plug in. I'm going to go ahead and solve and then plug in this case. I'm solving for P2, so what do I need to do? I need to get T2 out of both sides. So I multiply it on one side, I multiply it on the other, and I get that P2 is P1 over T1 times T2. Now I can plug in those things from my table up above. I have to scroll a little. It was 3 atmospheres of pressure was my P1. Here you have to pay attention to which ones are 1s, which ones are 2s, but this is why having the little table is nice. 373 Kelvin times 273 Kelvin. I type that into my calculator. What I would type into my calculator is 3.0 times 273 divided by 373. You type that into your calculator, and what do you get? You get 2.2 atmospheres. That 3 atmospheres there with 2 sig figs gets me my answer here with 2 sig figs. And there we go. Answer with units, work shown, canceling units, all the things that I need for someone to be able to follow what I'm doing. So that's how we solve a pressure and temperature problem. Here's one for you to try. We've got a system, it's initially at 20 degrees Celsius. We heat it to 100 degrees Celsius. The final pressure was 1.5 atmospheres. What was the initial pressure? So pause, solve, and come right back. You're back. You solved it. Good job. Let's see how you did. We see two temperatures. We know temperature is changing. We see a pressure, and it's asking for a different pressure. We know pressure is changing. So we've got this equation. P1 over T1 equals P2 over T2. We make ourselves a little table. P1, T1, P2, T2. P1, our starting pressure. Oh, that's what we're asking for. There's a question mark. What's our initial temperature? It was initially at 20 degrees Celsius. What we need to do, we need to add 273 to convert that to Kelvin, and we get 293 Kelvin. P2, that's my ending pressure, 1.5 atmospheres, and 100 degrees Celsius. But what do we need to do? We need to add 273 in order to get Kelvin, and we get 373 Kelvin. Now, we can go ahead and just solve this, or plug in first and solve next for this one. We're going to get P1 over 293 Kelvin equals 1.5 atmospheres over 373 Kelvin, just plugging in from our equation up above. I need to get P1 by itself, so I got to get multiplying by my 293 Kelvin. And I get that P1 is 1.5 atmospheres times 293 Kelvin, divide by 373. I type it in my calculator this way. And if you type that into your calculator just like that, what are you going to get? You are going to get something that I've got to calculate because I didn't have it in front of me. 1.5 times 293 divided by 373 gives me 1.178. What are my units? My kelvins canceled, and I get atmospheres. 1.178 atmospheres, but how many sig figs am I allowed? 2 sig figs from my 1.5 up here, 2 sig figs down here, and so I get 1.2 atmospheres, or D up here. Now we also want to think to ourselves when we get these answers, did it make sense? Right? I had a system that I heated up, and the pressure was 1.5 when I was done. As I heated up, the pressure should have gone up, so my initial pressure should have been lower, which it was. 1.2 is less than 1.5. Those are wonderful checks to do for yourself on your work, just an intuitive check. Because if the pressure didn't do the right thing, then you know you made some little mistake in your equation. You maybe put the starting and the ending ones in the wrong spot. So it's a good check to do, and I always like to do that when I'm solving things. All right, our next one, temperature and volume. Temperature and volume is an interesting one. It's the hardest one to think about. But what are we going to do? If we've got a box here, in fact, let's not draw a box, let's draw a cylinder that has a movable top. So this little top can go up and down. And right, if we've got gas in here, this top can just rest on top of the gas, right? And if it's movable and it's really easy, right, I could actually take my hand and push on it, right? And I could make that volume go down. Now, that changed the pressure. By pushing on it, right, force over area, I changed the pressure up here. And that's not what I want to do. Because remember, when we talk about temperature and volume, we're also talking about keeping pressure and moles constant. Right? So how do we keep the pressure and the moles constant? Well, if this guy can move, let's just heat this guy up or cool him down. Let's say we cool it down. Now, if we cool it down, what's going to happen, right? These molecules are in here. The reason it can hover on top of here is because some of the molecules hit the top here and they're pushing up on it. But if I slow them down, if I've got the same system here and these molecules are slower, they're going to hit this top thing much, much less, right? And if they're hitting it much, much less and much slower, they're not going to be able to push it as much. And so now this top is going to fall down a little bit. Before it was up here, and now it's down here because there's not as much pushing up on the inside. Now, how far is it going to push down? It's going to push down, turns out, until the pressure on the inside and the pressure on the outside are equal. And so we've kept the pressure the same by just using a movable top, which is kind of cool. But what do we find? As we took the temperature down, as we cooled down this second one, we found that the volume went down as well. And what do we have? As one goes down, the other goes down. Also, as one goes up, the other goes up. This is another direct relationship. And when we have a direct relationship, we end up with an equation that looks like this. V1 over T1 equals V2 over T2. And we're going to use that to talk about our relationship between volume and temperature. It's called Charles's law, if anybody ever asks you. And we're going to take a soda can that's got 255 milliliters of volume. We're going to heat it all the way up to 500 degrees Celsius, let it cool down to 0 degrees Celsius, and check out what happens to the volume of the can. Again, assuming the other things are constant. The pressure is constant and the moles are constant. So we see that volume's changing and we see that temperature's changing. So we know we're going to be using this equation, V1 over T1 equals V2 over T2. We make our little table because that's what we do. V1 T1 V2 T2. And what's our starting volume? Our starting volume is 255 milliliters. Now, do I need to convert that to liters? I said the most common unit we use for volumes is liters. And temperature, I said we had to convert to Kelvin. What about that milliliters? And the answer is no, because 0 milliliters means 0. And so it's a perfectly valid unit to use. It just means if we have milliliters over here, we've got to have milliliters over here. So if we were given two volumes here, and one was a milliliter and one was a liter, we'd have to convert that so they're the same unit. But it just means that if we solve this, we're going to get milliliters as our answer in V2. Our initial temperature is 500 degrees Celsius. How do we know? These two are correlated in the English, right? Our soda can had a volume of 255 and we heated it to 500, right? What do we have to do to that? We have to add 273 and we get 773 Kelvin. Our V2, that's what we're looking for, so we put a big question mark there. Our T2 is 0 degrees Celsius. We add 273 to get 273 Kelvin. Now we can go ahead and plug that in. Let's go ahead and solve first. V1 over T1 equals V2 over T2. We're trying to solve for V2, so we've got to get it all by itself. We multiply both sides of the equation by T2, and we get that V2 is V1 over T1 times V2, times T2. And then we just plug in our numbers from our table up top. V1 is 255 milliliters, T1 is 773 Kelvin, and T2 is 273 Kelvin. Our Kelvin cancel. We're ending with milliliters, which is what we wanted to do in the first place. And what do we find? We find that we get 90.05 milliliters. How many sig figs are we allowed? We're allowed 3 sig figs on this guy. Remember, when we have temperatures, we kind of ignore their sig figs. Temperatures and sig figs are a little bit difficult, so we're going to do our sig figs from everything else in there. We get 3 sig figs, and so we get 90.1 milliliters, just like that. All right, so that's our relationship between volume and temperature. And our last one, relating volume to moles. This one's pretty easy to think about. If we start with a balloon, and we haven't filled it up yet, right? The balloon has very little volume, but as we add moles, as we blow into the balloon gets much, much bigger. So as we go, right, it makes the balloon bigger. So as the number of moles went up, as we add moles to the balloon, the volume goes up. And we have a direct relationship, and we get V1 over N1 equals V2 over N2. This is called Avogadro's law. You remember Avogadro from Avogadro's number, the 6.02 times 10 to the 23rd. We're going to have a balloon with 1 mole of gas, and it takes up 22.4 liters. And how many moles of gas would we have left if we let gas out and the volume went down to 5.6? We see volume and moles changing, so we decide to use this equation. We make our little table, and it looks like this. Okay. My starting volume, 22.4 liters, and when it was, wow, that's really awful, 22.4 liters, much better. And when it was 22.4 liters, it had 1.0 moles of gas. And then the volume went down to 5.6 liters, and we're looking for those moles. Now, again, we can plug in and solve, or solve and plug in. I'm going to go ahead and solve first. It's my favorite way of doing things. And so we get V2 over N2. How do we get N2 all by itself? What I see all the time is I see students divide both sides by V2, and they get that here, and they get that over here. But if you do that, it crosses out over here, but it turns out what you're left with is 1 over N2, not N2. And so this doesn't really work. You can't do 1 over V2. You end up with an incorrect answer. So what we have to do is we have to get the N2 on top. A few different ways of doing that. One of the easiest is to do cross multiplication. And so you get V1 N2 equals V2 N1. Now we can solve that for N2 by dividing both sides by V1. And so we get something that looks like that. And the V1s cancel, and we get that N2 is V2 N1 over V1. And then we can plug those numbers in from the equation up top. What does the equation look like, or from the table up top? V2 was 5.6 liters. My N1 was 1.0 moles. And my V1 was 22.4 liters. And you can see it can get really confusing to know which things to put in when you're solving some of these equations, which is why having a table is really nice. You just copy stuff out of the table and you don't really have to think about it too much. And so if I go ahead and plug that into my calculator, I'm just going to take 5.6 divided by 22.4. I can ignore the 1. I get 0.25. What are my units? My liters cancel. I get moles, which is good because I was looking for N2, which is units of moles. And I found that as my volume went down, my moles went down, which makes a whole lot of sense. So those are our 3 primary relationships that we have: pressure and volume, temperature and pressure, temperature and volume and moles. And those are our primary gas laws. But one of the restrictions we had on all of those is only 2 things could change at once. We said, hey, if I'm changing volume and moles, then the other 2 have to remain constant, the pressure and the temperature. But oftentimes these things change altogether. And so what we're going to see in a little while is what happens if we've got more than 2 things changing at a time. But first, let's do an example. We've got a balloon of volume 7.28 liters and 22 degrees Celsius is heated to 45 degrees Celsius. We want to know what's the new volume of the balloon. So pause, try to figure this one out, and then come back. All right. Now, did you get the trick? I was just talking about volume and moles, and I didn't give you a volume moles question. What did I give you? I gave you a volume and temperature question. Those are the only things that are changing. And so I need the volume and temperature equation. V1 over T1 equals V2 over T2. And I make my little table, and it looks like this. And what do I put in? My initial volume, 7.28 liters. My initial temperature, 22.0 degrees Celsius. I add 273 to that, and I get 295 Kelvin. My V2, that's what I'm looking for. My T2 is 45.0 degrees Celsius. I add 273 to that, and I get 318 Kelvin. And just like that. And, excuse me, what do I do from there? Well, I'm solving for volume 2, right? So I plug in and look at my equation again. V1 over T1 equals V2 over T2. I want to solve for V2, so I've got to get rid of T2 on both sides. And I get that V2 is V1 over T1 times T2. And I plug in those from my little table. Volume 1 was 7.28 liters. T1 was 295 Kelvin. And T2 was 318 Kelvin. And what do I find? My temperature, my volume 2 was 7.28. I don't have this one again in front of me. Silly me. Was 7.28 times 318 divided by 295 is 7.84759. What are my units? Kelvin cancel. I get liters. How many sig figs? I'm going to ignore the temperatures and do 3 sig figs from there. 7.85 liters is what I get, and that is answer D down there. So when you're doing these problems, look at your variables, look at what's changing, and pick the right equation based on what is changing in your system. All right, one more thing to look at. What happens when we combine all of these laws, right? We had P1 V1 equals P2 V2. We also had P1 over T1 equals P2 over T2. And the same thing for volume. And it turns out we can combine them. If we're changing pressure, volume, and temperature at the same time, we can have this thing that's called the combined gas law that looks like this. Now, the nice thing about the combined gas law is it actually covers all three of them. Let's say temperature doesn't change. If temperature is the same on the left as it is on the right, it cancels out and you get P1 V1 equals P2 V2. If the volume doesn't change, it cancels out and you get P1 over T1 equals P2 over T2. So it's kind of a nice summary law. But let's go ahead and do a problem with it, because doing problems is how you figure out chemistry. You don't figure it out by thinking about it, you figure it out by doing it. I've got a balloon. It's filled with 1 atmosphere, 20 degrees Celsius, and the volume is 7 liters. A pressure decrease to 0.6 atmospheres, and temperature down to minus 5 degrees Celsius. I'm looking for the new volume. So I've got pressure, temperature, and volume, and all three of them are changing, because the problem says pressure decreases, temperature decreases, and I'm looking for a new volume. That is this equation, P1 V1 over T1 equals P2 V2 over T2. We make ourselves our little table. P2 V2 T2. All right, what's my starting pressure? 1.0 atmospheres. My starting volume, 7.0 liters. My starting temperature, 22 degrees Celsius plus 273 equals 295 Kelvin. What's my ending pressure? It is 0.60 atmospheres. My ending volume is what I'm looking for, and my ending temperature is minus 5 degrees Celsius. We add 273 and we get 268 Kelvin like that. Now, remember, we can use whatever pressure units we want, whatever volume units we want, as long as they're the same. If I had given you one pressure in atmospheres and the other in torr, you would have had to do a conversion to make sure that they're in atmospheres or torr on both sides. Doesn't matter which, but you got to pick one and convert them so they're the same on both sides. Now, I'm looking for new volume. I'm looking for V2. So how would I solve this equation up here for V2? Well, I want to get rid of T2, and I also want to get rid of P2. So I'm going to multiply both sides by the same thing, which is T2 over P2. It cancels on this side and just leaves me with V2. And I get that V2 is P1 V1 over T1 times T2 over P2. And luckily we have this table and we just look things up. Imagine if you're still trying to do that kind of plug in from your head thing, it can get really confusing. So I love having this table because P1 is just 1.0 atmospheres. V1 is just 7.0 liters. And T1 is 295 Kelvin. And then I multiply by T2, which is 268 Kelvin, divided by P2, which is 0.60 atmospheres. What would I type in my calculator? I would type 7.0 times 268, divide by 295, divide by 0.60. Remember, if you don't use the parentheses, just everything on the bottom gets a divide, everything on the top gets a multiply. If you type that all into your calculator, what you should find is you get 10.6 liters, which is great. We were expecting a volume. My atmospheres cancel, my Kelvin cancel. I do end up with a volume there. How many sig figs? Well, if you look up there, I've got several things with only 2 sig figs. And so that's going to look like 11 liters or 2 sig figs. So what happened? Right? I took it up a mountain, pressure decreased. My volume got bigger because as pressure goes down, volume goes up. And then temperature decreased, which should have made my volume get smaller, but who won? My volume was 11, even though it started at 7. So even though I had one thing trying to go up and one thing trying to go down, the pressure really won in this case. So sometimes we can guess what's going to be happening. If we have a situation where 2 changes we're making should both increase temperature, then we know the temperature is going to increase. If we have a situation where 2 things we're doing both decrease pressure, then we know the pressure is going to decrease. If one of them is going to increase, one of them is going to decrease, we usually have to do that calculation to figure out what's going to happen. All right, last slide. Here's a test of what we just said. If temperature goes up, but the volume goes down, what's going to happen to the pressure? So take a moment, think about that, come back to the video. All right, so if the temperature system goes up, what's going to happen to pressure? As temperature goes up, those guys move faster, they hit the walls more often, pressure should go up. So as temperature goes up, pressure should go up. And as volume goes down, as we squeeze it, the pressure in there, there's the same number of molecules now hitting the walls more often because there's less space. That also makes the pressure go down. I'm sorry, the volume go down, so that makes the pressure go up, which means two things making the pressure go up means absolutely the pressure is going to go up. So those are our gas laws. Lots of different ways of relating all the different variables, but important for being able to calculate changes when we do things like breathe in, breathe out, and all that kind of stuff. We'll be using those in all sorts of examples in the homework and obviously on quizzes and things like that. So make sure you know how to manipulate each one of those equations, solve for the different variables, keep track of sig figs, and show all your work. Thanks.